hand it over to you, Doctor. Please take us through your thank you.
Okay, thank you so much, Chairperson, and thanks, colleagues, both physical and virtual, for making now time to be here for this brief technical presentation. As I've been introduced, my name is Udochukwu Bola Akuru. I am affiliated to Tshwane University of Technology, and I will be giving a talk in my mostly research interest area, which is on the design of electrical machines. And the topic of this presentation is insights and potentials of one-field flux modulation machines for renewable energy technology. So this is the brief outline of what I will be looking at this morning. First, I will start with a background of where we are sitting in terms of the technology, where my interest is particularly is in applying these machines that I want to talk about. The motivation basically for this, considering these machines in my research area. Then I will take you a little bit back to the classical electric machine design theory and how we can link it up with these new types of machines called flux modulating machines and see the need why we can have some interests and perhaps see what the industry can also gain from their maybe their pros. Of course, there are cons about them as well. Then I will delve in more into the particular topology that I look at in terms of excitation, which is the one-field excitation machines, for the simple reason I will also emphasize during this presentation. Then I talk about the design evaluation we are doing briefly, the technology evaluation that we've been able to do with some of these machine variants, a future outlook, as well as a brief conclusion. Okay, so just to start with, renewable energy, as we know, have its advantages. I apologize if there are people who are not proponents of renewable energy here, so I'm not going to talk about their disadvantages, but for now, we look at the advantage, which is that they are clean sources of energy, and also they are emerging. I was listening over the radio, was it yesterday? So there is a global call for countries that are developed to, be emphatic about their transition plans to renewable energy by the year 2035. So it's an emerging technology. Well, maybe it has transited that stage, but it's still an emerging because it is not generally established in terms of its industry proportion. So we also know it promotes energy security through democratization of these energy sources. We can easily locate stations where we can generate, especially in my own case, power and transmit to consumers. We can also see the fuel is free. So there is not going to be any preferential advantage over some economies, for some economies over the others. Then, of course, we know it is flexible in terms of the way we can connect them to the grid and as well as operate them off grid. And we can have a system where it operates in both directions, by the way. Okay, so let me first of all take a deeper look into the electric vehicle sector, which is one of the areas I apply these machines. As at last year, the market value for the electric vehicle reached close to $382 billion US dollars. That's quite a lot. So you can understand the reason why most of us are actually looking into that direction. There's a lot of money there, although we are still expecting those money to come to us. There is also the rising demand of electric vehicle lately in terms of its industry outlook. So as you look at the figure shown on this slide, you could see that from 2016 to 2022, the industry penetration has increased drastically. Okay, But when we look at electric traction vehicles, one of the important components is the electric vehicle motor. So in this slide, basically what you see is some conventional motor technologies used in this industry, your permanent magnet as well as your induction motor. So the green, of course, means the good ones. We are going green. The red means the ones, the places where there are comparative weakness. So if you look at that particular chart, the most important thing here is a permanent magnet. I think it ticks most of the boxes, especially for the interior permanent magnet machine. So that's the one that is more popular. I understand that Tesla, for example, when they started with the induction motor, but currently they are also looking at, they are now working with the permanent magnet machines. But the issue is that permanent magnet motors, although they possess high torque density, they are prone to environmental issues in terms of their mining, high cost in terms of their material, and the risks of the demagnetization when they are operated beyond some certain limits. So this is why we want to consider alternative traction motors. Of course, the induction motor is there. They have the disadvantages, and the switch reluctance motors and the synchronous reluctance motors as well, which have their advantages and disadvantages, especially for the, what do we call them? The double salient motors with high torque ripple and as well as noise problems. So, but as I go into the wind power, we also see a growth in the sector right from time. So I think currently should be getting up to 1,000 gigawatts in terms of the global wind power capacity. So it's actually growing. And another thing we see is that the raw materials used in that sector is also mostly permanent magnet based, but I will talk about that later. But these are some of the reasons why I'm interested in this area in terms of renewable energy, electric vehicle, and wind power. So as we know, for wind power, the electric generator is a major component there. So in this slide, we just want to look at the trend from where we started and where we're currently sitting at. So over the years, what we see, we have moved a bit from the fixed speed systems to the variable speed systems. And the issue with the variable systems is that as we transition, they become fully dependent on the power electronics. So it is also a major concern in the industry. I just have to emphasize that. So the shaded cycles there shows current wind turbines, how they have become very large, and how they have become more dependent on power electronics. The other thing is in terms of the size of the components. So with a bigger turbine, the generator also becomes much bigger. Okay, so looking at the drivetrains also with wind turbine, so what we have seen over the years is that there's now a shift from the geared system to the gearless system. And the reason is just because of reliability. With the gearless system, there seems to be a higher reliability factor. The other issue is because LCOE, which is the levelized cost of energy, is much better with large-scale wind power, which usually goes offshore. And for that reason, you also want to have a system where so many things are involved, like logistics, maintenance, and the others. So that is the trend. So currently, we are sitting somewhere right here. If I can get my pen. So currently, we are sitting somewhere right here. You could see the gearbox has completely been removed. But before that, we have the high stage gearboxes and the medium stage gearboxes. And they both have their pros and cons. So, but what you can also observe is that as we go low speed, the size of the generator becomes much bigger. And if we depend more on permanent magnets, there are some issues which I'm going to show you as we proceed. Okay, so this also is just to emphasize what I've been saying. The industry outlook is going towards the large-scale wind power generators because they provide more output per cost. And the idea is to get them as big as 20 megawatt. But currently, I think the largest one industrially is 16 megawatts, which takes about 242 meters in terms of tower height. So I think that's the largest one for now in China. So, but the trend is to make them super large so that we can get more power. With this kind of systems, you can feed hundreds and thousands of households based on renewable energy. Okay. Now, looking at the fact that the industry in terms of wind is turning to large-scale direct drive, permanent magnet, synchronous generator solution, what are the highlights? So for such large-scale direct drive systems, we see that the generator performance is better. We see that maintenance is better. We see that generator and gearbox design weight, there is a trade-off, so it's also better. We see that the offshore trend is also useful for it. But there are two things that, I mean, we have to highlight, and that is in terms of their dependence on rare earth permanent magnets, which also affects their overall cost. So that is just a problem. Otherwise, that is the trending technology in terms of wind power generation. And for me, that is what motivates the research. So I go into the motivation. So having looked at the electric vehicle motors and looked at the wind power sector, which are just some sectors in the renewable energy industry, my motivation is that 50% of the world's neodymium permanent magnet material, which is used mostly in the rare earth permanent magnets, are mined in China, with over 90% of these used to produce these permanent magnets. As at 2011, there was a market hunch, which led to artificial scarcity of this material. And the graph you are seeing on your screen shows the amount of inflation, that is 2,500% inflation, just within a space of a few months. And I think that was just about the same time I started my PhD. I started my PhD in 2014, and there was a craze for alternative wind generator technologies. That is why I focused more on non-permanent magnet solutions. So we also have to emphasize that with permanent magnet, there's also the possibility of demagnetization in certain performance regimes. Then maybe some of us are not aware, there are also environmental and public health concerns as regards to how these permanent magnet materials are being mined. So because of these reasons and some other reasons also, when we look at, okay, maybe the argument is, okay, well, if you say the permanent magnet synchronous generator is not good enough, then let's go electrical excited. But with the electrical excited, I will still say that is a conventional technology, that it results in much heavier as well as much larger technologies compared to the PMSG in terms of torque. Of course, they use slip rings and brushes for their excitation, which brings some problems also in terms of cost and maintenance. Because of the field winding being used there, the electromagnets, the efficiency is also not that good. Then there is not so much interest in the industry to develop them. I think for now, it is only Vestas that are using these solutions for wind power, large-scale wind power generator. Okay, so now I come to the electrical machine design theory. So why have I said what I've said, and why am I here? So let's go back to the electrical machine design theory. So every electrical machine designer's interest is in terms of this performance metric, which is torque density, not power, but torque. The reason is because to design an electrical machine, you need torque. So this is your torque rotor volume equation. And clearly we see it depends on three things. Maybe it's not as clear here, but in the next slide. But for now, one thing that is clear here is that it depends on volume, which is your diameter as well as your stack length. And over the years, for the last century, we have seen that this particular performance index have been improved 100 times. So are we at the soft spot? Are we at a good point where we feel, okay, I think we've achieved a lot and we don't need to bother anymore? So that is what I want to delve into. We can still push this further. So with the classical electrical machine theory, torque is basically based on three things: magnetic loading, electrical loading, as well as machine volume. So if you want to affect torque, which is always our interest, we want to tamper with these three parameters: the magnetic loading with the source of the excitation, the electrical loading which deals on the load in terms of the armature, and the volume of the machine which deals on the material you use in designing, or the space where this machine sits in. So, and for that, we know it will depend on this same parameter which speaks on the volume. So this one speaks on the volume, which is diameter and the stack length. AS is the electrical loading, which speaks on the current carrying conductor, while BA speaks on the magnetic, or BG rather speaks on the magnetic, the magnetic loading. So there are pros and cons if we try to touch any one of them. So for example, we say, okay, let's increase volume so that the torque of the machine increase. Our machine becomes more bulky, more expensive, and poses manufacturing, maintenance, as well as logistics issues. So we know for very large scale machines, like I showed us, 20 megawatts wind turbine, it becomes very difficult to transport them right into the ocean where they may be needed to operate. So, and some other issues when there are maintenance, the expense that it brings about and all those things. So, but if we look at, okay, let's tamper with the electrical loading, we will increase costs as well, because losses will increase. Then we need to concern ourselves about what new or innovative cooling measures or expensive cooling measures we need to adopt. And also it leads to saturation issues, which reduces the performance. If we say we want to increase the magnetic loading, that, of course, will also lead to more costs, because, for example, it means you need more permanent magnet materials, which means more cost and stuff like that. Okay, so on that basis, the classical electrical machines torque equation suggests that the poles of the magnetic field and that of the that is the poles on the stator and as well as the rotor, just to put in a simple terms, must be equal. Hence, we don't usually see it in the classical back EMF equation, which is this. So you could see here the number of poles on the stator and the rotor defined by PR and PS are not indicated. But we can expand the equation to show you that those poles are actually there. So the only thing is that they are the same, and hence they cancel out. So if PR is equal to PS, then it's 1. So, but it is always there. So that is what actually will lead me to the next thing I will be talking about, that with a regular machine, whereas PR and PS is always 1, and it has never been an object of interest in terms of increasing torque density, can we sort of tamper with these values, make PR not to be equal to PS, and see what impact it will have on torque performance? So that it leads me to the next thing I want to talk about, which is this machines, by the way, the so-called flux modulating machine. So can we have a situation where these two poles cannot be the same? And please have in mind that, I mean, these are just magnetic fields, right? So with different magnetic fields, you have a vector. So the poles are necessary, especially for electrical machines, to be the same in conventional machines, so that you can get that torque, right? The rotation. So, but can we still achieve rotation? Can we still have torque performance without these two guys being the same? Well, let's see. So let's go back to the conventional equation where we said that PR cannot be, should be equal to PS. And we say no. Of course, they can both differ. So if they both differ, how can we achieve that? And what will be the outcome? So right on your screen here, the only way we can achieve a situation where PR cannot equal to PL, that's the pole pair on the rotor and the pole pair on the stator not being the same, and still able to achieve a machine that operates, and by the way, produces high torque density, is by introducing a flux modulator. So when we separate, embed a modulator between your armature as well as your field excitation, we basically able to disrupt the pole pairs on the stator and the rotor, and thereby achieve a machine that produces higher torque density. So what you have here, so for example, this is an 11-pole machine. So we introduce a flux modulator with 12 poles. And if you understand what modulation simply means, especially in power electronics, it sort of modulates the waveform. So basically that is what you have here. So you could see 11-pole field, 12-pole modulator, and 1-pole armature. So we have been able to convert the armature pole from 11 to 1. And what that means basically is that we have a slower moving magnetic field. And because it's slower moving, it produces more flux. And by so doing, torque is increased. So remember, it is torque density we are working at. The power is not changed, still obeys the theory of energy conservation, but torque is increased at the same space. So you still have the same volume. You didn't tamper with the electric loading. You didn't tamper with the magnetic loading. You basically altered the pole number of the magnetic loading on the stator to achieve this high torque performance. And for example, if you look at this, so this is your 11-pole, you can see the harmonic, the 11th harmonic on the stator, on the rotor. But when we introduce this modulator, what we are able to produce, we produce some interesting harmonics. If I'm not mistaken, that is number 1, and that is number 13 and number 11. So you can see number 1, number 13, they resemble number 11, which was the original harmonic, working harmonic. So we call these working harmonics. When we sum them up together, that is how we get the high torque density performance. So here is your classical equation once again. So basically what we introduced to what you have always known is a so-called gear ratio, which is facilitated by the flux modulator. So where the magnetic loading is facilitated by the field source, electrical loading is facilitated by the current, machine volume facilitated by the core materials, your gear ratio is now facilitated by what we call a flux modulator. So it basically amplifies. It works like a mechanical gear, but this time it's an electrical or magnetic gear. So what it does in the equation, as you can see, the same equation, we only introduce your PR over PS, which has always been there, by the way, just that they cancel out. In this case, greater than 1. So we're able to achieve high torque on the same volume. Please take note, other parameters here have not changed. And this is what this machine is, and that's why we call it flux modulating machine. So what is the theory around this? So the theory is simply that the stator pole will now be a sum of the modulator pole and the rotor pole. So that is what alters it. And also the magnetic gearing effect will be introduced. So the flux modulating machines works on the principle of flux modulation as well as magnetic gearing. And we have been able to show, or rather see, because colleagues have been able to show that we can achieve up to 150 kilonewton meter per meter cube in terms of torque density in low speed applications for these machines. So what happens is that if you have a high pole pair of your modulator, you are able to achieve high torque density performance based on the relationship shown. So in terms of topology, nothing changes. So remember, when we talk about torque volume, it's not specific torque. So we are still taking the envelope volume of the machine. So what we just need to do is to work within the space of that volume to see what to do. So we introduce, for us, if you have a regular machine, classical, which works by same pole pairs on the rotor and the stator, we now introduce your so-called gearbox system, flux modulator. I'm not sure if it's appearing clearly there. Then we get what we now call our flux modulating machine. So if you look at the first machine there, if you observe, it's a 4-pole machine. So, but if you look at this one, because we only show the flux lines there, you will see multiple poles on the stator. So it has basically transformed the pole from low pole to high pole, reducing the speed, increasing the torque. So it is the same thing as your bipolar junction transistors, by the way, those who work in power electronics. Okay, so let's look at the classification of this machine. So what are the possibilities? So the possibilities are so many. So they are new machines. There are so many, and we give them a lot of nomenclature. So, but we achieve them basically based on these 4 different manipulations. So it is either, so we say it is necessary that only one part of this machine should be stationary. But at the same time, it is required rather that only one part should be stationary, but it is not necessary. So we can have a situation where the 3 parts of the machine are all rotating. So you have your rotor, your field part rotating, you have your armature part rotating, you also have your modulator part rotating. So you have a machine maybe made up of 3 air gaps, and each part of it are rotating. So if you're able to achieve such a machine, you have even higher torque density. Sometimes we go to like 2 per unit, the size of the torque density you will achieve under the same volume and magnetic as well as electric loading. Okay, so let me just quickly bring you to what what I am more interested in with these machines. So I didn't develop the theory, by the way, so I only stumbled across it, and I felt it was interesting to see how to apply them in machine design, especially for renewable energy applications. So based on the motivations I've given already before, with the growing nature of the renewable energy industry, as well as the need to look for alternative electrical machines for that industry, I hereby present to you the so-called one-field flux modulating machines. So take note, it is possible to design these machines with permanent magnets. So they work like your normal machines. You can also have hybrid excitation sources with the permanent magnet and the one field. But I focus more on the one field because here in South Africa, I don't think we have the permanent magnet resource. So at least if I'm able to develop this kind of machines, I can build them locally and also market them locally or even export them. So that's the idea behind it. But the good thing about this variant of one field machines, different from your conventional electrical excited machines, is that when I take a conventional, in quotes, a conventional one field machine, your electrical excited synchronous generator or motor, and I incorporate the modulator, because there's need for a modulator so that we can transform the machine into a flux modulating machines. What we achieve is a one field flux modulating machines with 2 important features that we are hitherto not present in a conventional electrical excited one field machine, which is that this machine automatically becomes brushless. I can be able to transfer all the active current parts to the stationary member. And as you can see, the rotor becomes a robust member. So it's just a simple rotor, no windings, no need for brushes, no need for slip rings. And I can come up with a number of topologies based on what I've explained. So these are the advantages in a nutshell. The one-field flux modulating machines produce brushless DC excitation. So I don't need to invent any sophisticated means to achieve that. Just by the design of the machine, it becomes brushless, just like your switch reluctance machine, by the way, but different in terms of operation, because here we put the field on the stator. So it has a robust rotor structure for applications where you need robust rotor design. It produces high torque density. We can still achieve variable field control, which is usually important in some application area. And most of the time, the winding topologies can be designed as concentrated winding, which of course, as you know, will increase the performance in terms of efficiency. Then of course, it's more suited to low speed application, because for us to get high torque density, the speed has to drop. So that is basically, and so many other advantages, the reasons why I look at this machine. And I've looked at a couple of them. I've looked at the first one there. I've studied them. I've applied them in the renewable energy sector. I call that one. We call that one the one-field flux switching machine. So it works on the theory of flux switching. So the flux is switched on the stator, between adjacent poles to achieve back EMF production. And we have it in different topologies. I present to you two topologies. The topology here, I looked at my PhD. This topology, I was working more later after my PhD, and also some of my students lately. We also have the flux reversal machine, the one-field flux reversal machine. That is the one showed here. So you can see this one is an outer rotor design. So this one works on the theory of flux reversal. You also have your DC excited double salient machine. This one is usually the one that doesn't work that well compared to the others in terms of torque performance, but it's also possible the way we design it to achieve electromagnetic performance. Then you also have your vernier machines. Most of you will be familiar with your vernier machines. Your vernier machine, we can also design them as a DC excited machine. So, but the main problem that comes out with this kind of machines, so like I said, not to sound like a marketer, we still have the problem of high cogging torque, of course, because you see they are mostly double salient machines, and as well as efficiency constraints because of the introduction of the wound field. But that is what drives our research, and that is what we try to address most of the time in our study. Okay, let me quickly go to the design evaluation of these machines. So it follows the conventional method of evaluation, so nothing out of the extraordinary. The only good thing here is that you have new variants of these machines, so you can easily motivate for new contributions in terms of research. And it is not yet developed in the industry, by the way. So that is what we are driving towards. So we start, first of all, by specifying giving the technical specification of the machine, form new topologies where possible. I will show you a topology we formed, just a simple one, based on the double stator design, or you select based on existing topologies and align them to your design needs. We size them based on the torque rotor volume equation I showed you, and we create the volume and sort of evaluate them analytically as well as with the finite element method. So we are able to also optimize them based on a multi-objective and global optimization landscape. One aspect I've not touched on, which I know is also not that addressed in the field, is in terms of the structural analysis, but some studies are ongoing. And last year I was in Germany for a research visit. So the concern of my host was in terms of this area, that if we really want to push these machines to the industry, we need to address this point. So it's something I will also be looking at in the future, but some other colleagues are already working on it. Then, of course, typing, lab tests, and demonstration of technology. So the scope for me in terms of this design that I do is trying to move away from a conventional machine and a PM or brush-based machine to a non-conventional, non-PM brushless machine. I deal more on numerical techniques than the analytical methods. So mostly I only apply the analytical method in the sizing of the machines, but I do the numerical analysis even with the optimization. That gives a more reliable performance in terms of results, but sometimes it may be more expensive in terms of time. Then, of course, I also try to move away from just doing an experimental work to try to apply it in a specific area, especially with renewable energy. Okay, so these are some of the technology application of these machines. So like I said, this was mostly during my PhD study. We're able to design and build a 10 kilowatts one-field flux switching machine. We're able to test it. You can see the measured results with the predicted results, and they align very well. So this was designed for wind generator based on the medium speed wind turbine drivetrain. So with a gearbox, but not as big as your high-speed gearbox. So well, we got some interesting results, and we also did this study at utility scale at 3 megawatts. And you can always assess the findings from that study. So this one I was trying to do during my postdoc also at Stellenbosch University. So this one is a very interesting machine. It's the vernier topology of these machines. So once again, I just want you to see the robust rotor. So that's why we always say they are brushless, because you can see maybe if you notice here. So this is a fuel source on the test bench. So we just connect that fuel source straight to the field winding without needing brushes or slip rings. So we're able to test this at low load to get some interesting results. Because I left the place at the point to come to TUT, I couldn't finish this study. Some other students took over it, and they tried to also apply it in synchronous condenser application, which I believe SAIEE would have, this particular committee would have been acquainted with. I think my colleague, Dr. Mabula, made a presentation in the past on that. So currently I'm working with my colleagues in Pakistan as well as at Wits University. So this is a new topology I propose, the double stator, one field flux switching machine design. So remember, like I said, with the one field, you don't get as much as you get from a PM design. So what we have noticed, especially in my PhD study, is that as we try to go very big with these machines, we create a big bore on the rotor. So most times that bore is just there, and it will not be too economical to design a rotor to fit in that bore. So what we try to do is to put another machine into that bore. So that's what brought about this. So remember, the torque density is still, the torque density is improved by that thing, because the what's it called, the envelope volume is still kept the same. So that was the motivation behind this. So we introduced another stator, which we call the inner stator, to boost the torque density. And currently we tested the machine, is working well at Wits University with Dr. Lesedi. And that's the one we are working with, and we've prototyped and we've developed it. All of these things we have built and developed locally in South Africa. We didn't need to import any material. I work on this mostly with my colleagues in Pakistan. So here is another interesting concept, and there's a lot of topologies. These are just the ones we are looking at. So this one is called, once again, the one field flux switching machine, but with a dual rotor. So this is not a dual stator, but a dual rotor machine. So once again, dual rotor because the rotor is robust. So we don't need to put any windings on the rotor, just one stator. And very interesting also, he was able to design it for a counter rotating wind turbine. So it rotates this way and this way. So it increases even more the torque density performance. This is one other thing we stumbled across when we were working on these machines, that since we have a robust rotor, and we were able to find out that these rotors can yield very high inertia, we're able to apply it in a synchronous condenser application. And we did some theoretical study even for very large synchronous condensers, 250 MVA. And we did some experimental study, and it worked perfectly like an electrical excited synchronous generator. The beauty of this is that maybe colleagues in power electronics will not agree with us, but as we begin to penetrate renewable more into the grid, and the concern for inertia and all those things are there, we can always use these machines to buffer the grid in such instances. Also, not only for, somebody had a good question earlier on that, why is all the interest about the generators. So of course, that's my interest area. But of course, because I'm also now looking at the motor application, and more recently also for industrial motors. So this is a study we use this machine to perform on industrial motors. So we compare it with a with a squirrel cage induction motor. So as you can see, the efficiency is higher, like it would be for a conventional electrical excited synchronous motor. We also do the dynamic performance and also the torque. So this guy is the torque. You can see at the same torque, we're able to achieve higher efficiency. So this is one of the things we are able to use these motors to do. So even for motor application, we can also apply this. Once again, they don't need slip rings and brushes. Okay, so what is the future outlook? So there is a lot of topology. So I just pick some of these from other colleagues, what they are doing to show us the possibilities. So there is the so-called partition stator multi-tooth design topologies to improve in terms of the acoustics, reduce the noise, improve on the torque ripple. There is the axial flux design to increase the torque density. The last time we had a presentation, the colleague mentioned about the axial flux machine. So we can also design these machines based on the axial flux topologies. We can also incorporate innovative windings like the Leeds wire has been incorporated into this machine to boost the performance. There are also the dual mode machines where you have dual electrical, dual mechanical. There is also new winding topologies where you have high temperature superconducting machines, materials being used for the windings, or carbon nanotube windings, and so on and so forth. So there is a lot of options available, and some of these studies are mostly experimental, but shows interesting results. Also, we have what we call the magnetless double stator, double rotor machines. It is mostly what I do. So that's things that are still there for us to explore. There is a non-radial flux machines. So mostly the ones I've been looking at are the radial flux machines. So we can also have the axial flux, like I said, or the transverse flux machines with the advantages also in terms of torque density improvements. There is advanced novel winding designs based on superconducting materials, like I've mentioned. And of course, there is the renewable energy application, which drives mostly what I do. So for example, recently I begin to look at it in terms of traction motors, especially in South Africa for the mining industry. So one of my PhD students is actually working on this. So, and if you understand, this is mostly that operating space, the yellow parts where we want these trucks to operate. And but most times this is not the high efficiency spot. So, but what we are hoping to show is that with these kind of machines, we can actually achieve high efficiency because we can vary the flux. So that is something we will likely able to show that, I mean, we can extend the efficiency performance regime. So what are the other research areas? The mechanical design and the acoustics is, I think, the last stage before the industry begins to, I mean, take us seriously. Not that some are not already looking at this. One of the study I showed you was done by ABB Research. I think in Stellenbosch, ABB was also involved with the vernier machine technology. So there are some industries already showing interest, but maybe not at the commercial stage. But hopefully, when we address some of these challenges, and it can fly. And I want to tell you, there is a lot that can still be done in this field because these are so-called emerging machines. Remember, your induction motors and your synchronous motors have been there for hundreds of years. So we are beginning to look at this, and there's a lot we can just duplicate that have already been done with the conventional machines. Okay, let me just quickly conclude by saying that the so-called one-field flux switching, flux modulating machines, which I've highlighted in this presentation, offer high torque density capabilities without a need for slip rings and brushes, making them well suited for the renewable energy sector. Understanding their theoretical operating principles as well as will enable electrical machine designers to effectively evaluate and optimize their design for maximum performance. With the rapid growth in the renewable energy sector, in terms of wind and electric vehicles, these machine variants, especially the one-field machine variant, present an exciting opportunity due to their high torque density, efficiency, and robust performance. Their development adoption can also support our national as well as global transition to sustainable energy systems. The research potential in this area is quite large, and it begs for all our attention and expertise. Okay, thank you very much. That's all I have to offer. I want to acknowledge some of my collaborators and funders, as well as my students. And these are some of the references I used for this presentation. And these are some of my publications based on this particular research area. Thank you.
Then we'll go to our virtual audience. Any questions on the take? Okay, so just maybe I can ask one. It's a little very interesting.